This is Chapter 4, Hypothesis Test. We will do more in Chapter 5 and, well, the rest of the class on testing hypotheses, but we're going to sort of give a broad overview in this section. Hypothesis testing in most of science is invalidating something. We come up with something called the null hypothesis, and then we see if the data disproves the null hypothesis. At least that's what we're going to be doing here. There are ways in which we point at data or use data to be more confirmatory and to point towards sort of positive affirmation. But what we do in classical science is that we test them. In the health cell book, it shows a variety of different types of graphs and then breaks them down basically on what kind of test goes with what kind of data. And we'll do that too. But I want to go first through this structure of a hypothesis test here, which I think is pretty important. Typically, here this is a little bit more limited than what we actually do. Usually we have this grand view of the world and these overarching paradigms of what's happening, and we decide we want to go test something, whether EMF radiation causes stunted leaf growth or there are heat island effects near airports or something like that. We have a hypothesis, and then we have to come up with an operationalized hypothesis. In other words, how are we going to gather data and test that? What kind of structure we can use to do it. Once that's sort of out of the way, then this approach here starts to kick in. We have to pick a test. We've already gotten our data. We've measured it. We're sort of stuck with the measurement at that point. Oftentimes you might think about which tests you're going to use beforehand. That's good. But often, other times, we went out, we collected the data based on what was available, what machinery we had, etc. And at that point, you're going to choose a test and review its assumptions, right? Because all tests out there have assumptions, and we'll talk about those more and more. If the assumptions aren't met, sometimes it just means your test and your results are going to be crap. Other times, they're just going to be a little bit suspect, and we'll talk about that. And then you're going to establish a null hypothesis, decide on an acceptable error rate. That's our 95% confidence interval. We're going to test it. We're going to look at the p-values, and then we're going to ask if the p-value is larger or smaller than our alpha. We're going to use 0.05 here. So we're not going to wander through all of the stuff in the health cell. Instead, we're going to go to our graphs to analysis, Chapter 4, the JMP version. We're going to look at categorical versus categorical, and I talk about input and output variables, or X and Y. Okay, typically this is the causal and this is the caused, but not necessary. JMP is very nice in that it chooses the test for you based on the type of variables. I'm going to walk through these, and then we'll actually go and do a few. When the input variable is categorical and the output variable is categorical, we have things like mosaic plots and pie charts and that sort of thing. Typically, in a fit X versus Y, we're going to end up with a likelihood ratio chi-square or a Pearson chi-square. The Pearson is more common, and a little later we will discuss how to do the Pearson in that. And then you can also use the little drop-down red arrow to give other measures of association and some non-parametric alternatives. Well, these are already non-parametric, so. The next we have our categorical X, continuous Y. Again, we're fitting Y by X. And in this one, we're going to use our little drop-down arrow, and we're going to check the ANOVA or t-test. This graph was not created in the ANOVA section. It was created using the graph builder, but you'll commonly see these kinds of graphs where you have a 95% confidence intervals or standard errors of the mean. Those are both popular, and then we want to know if there's a difference, a statistical difference between the two, and we use that using an ANOVA or a t-test. Sometimes when we think our variables don't really meet the constraints of the ANOVA or the t-test, when we're still in a categorical or continuous, we run a non-parametric Wilcoxon or difference of medians test. And those will give us whether these distributions are different. The medians will tell us if the medians are different, but they have some assumptions about symmetry about the median for it to make a whole lot of sense. And as you can see, these distributions are anything but symmetric about the median. This squinchy little line there is the median, and then there are tons of outliers that go on forever and ever. In this hares versus habitat, this is the count of mountain hares in alpine versus meadow habitat. Maybe they're easier to see in a meadow, I don't know. So that is another categorical bicontinuous. Then we move into continuous bicontinuous, and typically that's going to be represented with a scatter plot and a line fit, not always, but typically, because it makes sense, you have continuous bicontinuous. Here we are looking at the hypotheses that there is a relationship between how big the habitat area is and how many hares were counted. Clearly not a very strong relationship because some of them are way up here and some of them are out there. But we fit this, again, using the fit x by y, and we will use a linear regression approach and test that hypothesis. And the hypothesis we're testing here is that there's no relationship, and no relationship means the slope of this line is not significantly different than 0. So our null hypothesis there is that the slope of the line is 0. Here, the null hypothesis is either that the distributions are the same or that the median is the same. The null hypothesis here is that there's no difference between the means. The null hypothesis here is that in all of these boxes, quite honestly, should be the same size. And depending on the distribution of the categories, but that we shouldn't be able to see great differentiation across or up and down in the size of the boxes. These don't look like it's, and we get a very high chi-square and a very small p-value associated with that. And then there are a few more. When we have continuous bicategorical, it can go the other way. If it's if the categorical is binary, then, or two categories, then we use logistic regression, and we will do that later in the class. I just wanted you to show there's some of that. And we'll also do some predictive modeling or recursive partitioning where we get graphs like this. But this is predictive modeling, not in CAPS hypothesis testing. We can generate hypotheses after these, but in the classical model, that's not necessarily what we want to do, and it makes the hypothesis test a little sketchy. All right. In the next section, we're going to move through and just do these with a few data sets. Then it'll be your turn, and you'll have to do a graphs to analysis with data you choose.